So this is a worked example on how to transform a specific point on a function to another one, but this time we're working more in the abstract. So we're given this very general equation, and I'll write it up in the corner here. We have a times f of bx minus h plus k. Now this is going to look very similar to a lot of things we've done in other sections, but we're now finally abstracting this and saying that we can do this with any function ever, right? So what we're provided with is we are told that we have this point 2, -3 on the function f, and we want to find out where that point ends up on this new function that I have to find over here. So the way we're going to do that is we want to identify with our function right here what our values of h, b, k, a are. I think I said all of this correctly. We want to identify all of those values. And it's pretty clear if we compare the definition, we're only going to have two values actually. We're only going to have h and k in this case, and hopefully it's pretty clear that h equals 3 and that k equals 1. For more complicated problems, you may need to do a little more work, like you may need to separate some fractions or kind of look a little bit harder. But generally, we're just trying to write this function into the form a times f bx minus h plus k. And once we get that, we can write down the specific values. So then what I would recommend is to make a table. And this table won't be quite as extensive as some of the other ones we've worked with because we only have one point that we're using. And then just for the sake of this video, I will write out all of the values that we could use, right? So we'll have h, b, a, and then k. It's the order that the theorem works in. However, in our case, we're really only going to be caring about two of these values, right? Because h is 3, k is 1, b happens to be 1, but this isn't going to affect our values as we'll see in a minute. And then a happens to be 1. So if we follow through the theorem, we can see that the first step is to take h and add that to all of our x coordinates. In this case, we only are working with one x coordinate. So I just take 2 and I add 3 to it. That becomes 5. The y coordinate stays the same. The next step for b would be to divide b by the y coordinates. But if I divide something by 1, it just stays as itself. So I'm just going to draw an arrow to demonstrate that this value doesn't change. It's still going to be 5 minus 3. Next, for the value a, you would take the a value and multiply it by the y coordinates. Again, if I multiply by 1, I'm not changing anything. So again, I will draw an arrow to demonstrate that this is just maintaining, the same exact value of 5 minus 3 throughout all of these columns. And then the last step is to take that k value and add that to the y value. So now we do have some change. So I can take 5, comma, -2. So if I add 1 to -3, I get 5, -2. And that's our answer. We're not asked to graph or anything just because this is a pretty abstract problem. But we do know that if we're provided with this 2, -3 value, I know that 5, -2 has to exist on this function. And that's how you take an arbitrary point from an arbitrary function and use function transformations.